Hello, everybody. My name is Robert Amaro. I'm going to present on some work that we did for certifying components for hypersonic flight for folks in the United States. That's all I'll say about that. So somebody came to us and said, can we fly additively manufactured components, one-time use, hypersonic flight? And so that's our research question. The AM component will experience fatigue at elevated temperatures. It'll be manifested with machined and as-built surfaces. There will be re-entrant corners, so a KT approaching a K. And then the AM component falls within not super critical, but maintenance and durability critical criteria per American type mill specifications. So component is quite large. It's 23 centimeters, 13 centimeters by 4 centimeters. The massive component, AM718, with quite a bit of geometric discontinuities. In order to start this program, the first thing we did was determine under what conditions can we manifest material in a repeatable manner. That talk will be given at about 4 o'clock today by Ms. Bobo, and that's what this is. Qualified metallurgical process. How basically can we control this process to the extent that I can put my name on a flight piece of hardware for a hypersonic flight. Ultimately, what do we have here? What was I asked to do in particular? Need to determine the material's the deformation response. I need to be able to quantify the material's constitutive behavior. I need to then implement that within a solid model. So the solid model then must take into account, it's rubbish in, rubbish out. And especially with a hypersonic assembly, we have lots of interfaces, lots of interactions, lots of cycling, lots. So the boundary conditions and the loading conditions were non-trivial inside of the finite element solid model. First, can we capture the constitutive behavior? Second, can we implement that within a finite element solid model that incorporates all loading and boundary conditions? Third, can that assembly predict the current stress and strain of the component such that we can then predict life? Ultimately, Inconel 718, this is the microstructure. It was heat treated and hipped. It's created on a single piece of equipment. There were 40 pieces of flight hardware, all created from the single lot of material. It was very controlled situation. Here are the build platforms that we used to certify our process, to determine the constitutive models, to create the life model, and to manifest what we believe to be a repeatable process to produce Inconel 718. One top left shows one build platform, one third of a meter by 1/3 of a meter dog bone build. So 27 dog bones. The dog bones that you see near the center in blue with the blue lines, those are notched with a KT of 3. The flight components are shown in the next to the second to the left. So the flight component is built in the center of the plate with one microstructural witness sample and one dog bone. You'll notice on the dog bone builds, the flight component location was marked off. We are not building dog bones in the dog bone build in the location of the flight component. From the flight components, we then sectioned them up to create test specimens. We had 70 test specimens total, dog bones total. In the dog bone build, we will be looking at as-built surfaces, smoothed and notched. In the pulled from the flight components, we'll be looking at, again, but machined, smoothed, and notched. Ultimately, we will go over this at length at 4 p.m. But ultimately, what we found was that for strain life, we are manifesting two different deformation regimes. Number one, your baseline, machined at room temperature. Machined at room temperature provides you with one very specific response. Number two, machined at 400 degrees Celsius. So we took a life debit in the low cycle fatigue regime when we increased the temperature. But what you'll notice is that we took nearly the identical debit for the as-built. So whether you're 400C or you're as built, you take nearly the identical debit in life. And what's most interesting to me as a life modeler is these two life debits are not additive. Whether you're 400C as built or 400C and as built, you're basically of the same data. It collapses ultimately to the same thing. In order to do notch specimens, KT of 3, we conducted load control testing. Ultimately, by use of ASTM 739, we can show that our 95% confidence intervals are beautiful. And then we take that data and ultimately nice boring Chebauche, nonlinear kinematic isotropic hardening model inside of Abacus, in which we are looking at, well, I'm certain you're familiar with these, but ultimately we calibrate our constitutive model inside of Abacus by use of continuum mechanics and the Chebauche model. Top left shows the proof of efficacy for our constitutive model at room temperature. So what we see on the top left is our first cycle, experimental data in blue, predicted data in red, and then our stabilized cycle for this strain-controlled test. Bottom down here, we've got a separate Chebauche implementation. In Abacus, there's not a temperature-specific Chebauche implementation. You have to have different implementations, and then as long as you can linearly interpolate between those temperatures, the deformations manifesting at those temperatures, you can then apply temperature-specific manifestations. I'll discuss that a little bit more in a second. First cycle, stabilized cycle, we're capturing evolution of the material. Ultimately, though, I need to be able to predict not just the constitutive response, I need to predict the life of this actual component. So I can't show you the flight loading. I can basically say that there are two flight loadings that we are going to apply in order to, in an attempt to calibrate this life model. One loading has temperature increased to 300 degrees Celsius in a relatively short period of time. And it is load controlled, strain controlled, variable amplitude, can't discuss. It looks like fully reversed on purpose. Ultimately, we ran, in order to calibrate the life model, we ran two smooth specimens from these locations, KT of 1 and machined. Flight profile 2, again, two smooth specimens, KT of 1 machined. Then as built, flight profile 1, as built, flight profile 2. And this is our predictive, this is the Chebauche prediction of the stress relaxation within these specimens as a function of time. So in this particular case, what we're looking at is variable amplitude loading with varying temperature, and I'm predicting in the black dots the evolution of my material as a function of cycles. The actual material data, test data is in blue. You'll note, I'm not, wash this out. You'll note I'm missing some mean stress evolution effects, though. The compressive side, I'm missing. Ultimately, got a life model, and this is really the point of this work. Can we fly hypersonic hardware if we manifest hardware that we can trust? This is the life model that we selected. It's a physics-inspired dominant damage interaction life model. It takes into account material evolution, takes into account damage accumulation at room temperature, at elevated temperature, but then also, most importantly, the interactions of those two. The interaction of the damage evolutions is critical with thermomechanical fatigue. So with the data that you saw, we used that information, the strain-controlled data, and then the selected flight data to calibrate the model. So predicted on the bottom, the actual on the left-hand side. Now it's time for V and V. So specimens that we've not run yet. Notched, as built. So I've got notched in here, and I have as-built in here, but I do not have notched and as-built with a flight profile. So I take notched as-built with a flight profile, 4 of them. And then I also take 4 notched as-built, notched machined, whatever. As-built up top, machined on the bottom, total of 2, 4, 6, 8 tests. So these are 2 are my verification, 2 are my validation. Here we see the final results. So first thing you'll notice is that I way over calibrated my life model. Actual flight is very, very low cycle fatigue. But I was happy to do so. Second thing you'll notice is that well, our calibration data is, again, quite nice. The V&V data is okay. It's approaching the bounds of our calibration data. Not super happy about that. Nonetheless, it was sufficient to give go for very low cycle fatigue flight with these components. Conclusions, the deformation response of a well-controlled and well-documented AM IN718 part can be successfully predicted by use of nonlinear kinematic isotropic constitutive model. 2, when concerned with the deformation response of as-built and machined surfaces at 27 and 400 C, what we found for our material that we manifested through our process was that 2 constitutive model calibrations were sufficient. 1 that incorporated elevated temperatures and as-built surfaces, and 1 for machined room temperature. Physics-inspired life model, detailed, not really detailed, sort of brushed over inside here and calibrated for this particular material, predicts lives of the Inconel IN718 well. Then the model has been shown to be useful to predict the effect of non-isothermal elevated temperatures, varying surface conditions, varying loading conditions, varying geometric discontinuities. And with that, I'll open up the floor for any questions.